Okay, here's a simple RC circuit. A voltage source, two resistors, a three-way switch, and a capacitor. The switch is open for starting, and the capacitor is uncharged. And we're going to take the switch from position 1 and close it to position 2 and start the clock at t equals 0. So we're going to close this, we're going to start the clock, and for that we want to plot the charge on the capacitor versus time and the current through R2 as a function of time. And we want to show 3 time constants in the graph. And then once we've done those 2 plots, then you're going to take the position closed at 2 and bring it down to 3. So we'll switch from position 2 to position 3, and we'll restart the clock at t equals 0. And once again, we're going to plot QC as a function of time, the charge on the capacitor, and the current through resistor 2, also as a function of time, showing 3 time constants. So that's 4 graphs, 2 different situations. See if you can plot those, labeling the axes, putting numbers, and getting the shape as accurate as possible without plotting individual points. Once you've done that, you can go to the next page and check against what I did. Okay, I hope you were able to do it. Check your answers and see if you get everything right. So I rewrote the circuit here just so we didn't have to flip back to the other page. The voltages, the resistances, and the capacitance. Now to plot the thing, to make the plots, we need to know the time constant. And for the circuit where the switch is closed here, both resistors, current will flow from the battery through 2 resistors onto the capacitor and from the capacitor back and through the battery. So current is circulating this way everywhere except not between the plates. It's charging the capacitor because between the plates is an open space or an insulator. So the time constant we know is RC. So when we multiply the 40 millifarads by the 20 ohms, we get 800 milliseconds, or 0.8 seconds. So we have each time constant is 0.8 seconds for both of these graphs. And since this is 10 volts, the capacitor will charge until it reaches a voltage of 10 volts, and then it'll stop charging because the capacitor and the battery will be equal and opposite currents, voltages. So it will charge to a maximum value of, let me write that equation, Q max will be equal to C times V max. And C is 40, V is 10, there's your 400 millicoulombs, the maximum charge. So that's the charge it's going to get to. And it goes about 2/3 of the way each time constant. So it'll go to, just eyeballing it, it would be roughly, I think it's 0.63 actually, but roughly 2/3 of 400. Then between here and there, it'll go another 2/3, and then another 2/3 of what's remaining. And so it does this exponential charging. And after 3 time constants, I think it's at about 95% of its charge. Similarly, when the switch is closed and the capacitor is empty, the current, the there'll be no voltage across the capacitor, so by Kirchhoff's loop rule, there'll have to be 10 volts across this 20 ohms of resistance. And so you get a maximum current for this circuit. Imax is going to be equal to Vmax, the 10 volts, divided by the total resistance, R, 20 ohms. So 10 volts divided by 20 ohms, that gives us the ½ amp that I'm showing here for the maximum current. And as the voltage across the capacitor rises to 10 volts, the voltage across the resistors will fall to 0 volts. And at any point during the charging, the sum of the voltages across the resistor and the sum of the voltages across the resistor and the capacitor will equal 10 volts by Kirchhoff's voltage rule. So we start at ½ amp, come down 2/3 of that, come down another roughly 2/3 of that, and again decaying in 3 time constants to about 95%. Okay, so we've reached our final value of 400 millicoulombs and 0 amps, and the situation with the switch here becomes static. Then we flip the switch here and restart the clock, and now the capacitor is going to discharge, but this time it's going to discharge only through 5 ohms of resistance. This resistor will no longer be in the circuit. And so our new time constant is the 40 millifarads times the 5 ohms. That gives us 200 milliseconds, or 0.2 seconds for the time constant. The capacitor started, when it ended, it was at 400 millicoulombs, so it's going to start at 400 millicoulombs and decay about 2/3, about 2/3, about 2/3. So in 3 time constants, it'll lose 95% of its charge, coming down with a time constant of 2 milliseconds, 200 milliseconds, or 0.2 seconds. The current this time, since we started with 10 volts here, when the current first starts, it's going to be 10 volts divided by 5 ohms. So the current this time, because there's only 1/4 of the resistance, will be 4 times greater. And so the current will decay from 2 amps down to 0 amps, dropping about 2/3 of what's remaining each time, and about 95% discharged by the 3rd time constant, noting that the time constant is 0.2 seconds. And so that's the shape, and those are the numbers. Done.